At the plant growth stage, the fiber quality is affected by plant species, the crop production, the location, and the climate. The temperature at which the plants are grown, as well as location of the fibers, which will also influence fiber properties. And next is at the harvesting stage is mainly depends on harvesting time, age of plants, and also part of plants. And the fiber extraction stage involves some process of retting by which the fibers and the non-useful biomass are separated. And the right figure demonstrates the dependency of properties on their structural constituents. The properties of fiber reinforcement have a major influence on the properties of final product. As I mentioned before, the properties of the natural fibers are governed by their main chemical constituents such as cellulose, hemicellulose, and lignin. If the percentage of cellulose is more, it provides strength to natural fibers. Suppose if the percentage of hemicellulose is more in natural fibers, it leads to thermal degradation and moisture absorption. And this slide is on fiber extraction methods. The most common methods to separate the fibers from the plants are dew retting and water retting. Depending on the fiber category, these methods require approximately 14 to 28 days for the degradation of waxes, pectin, hemicellulose, and lignin. To reduce long processing time, alternative methods such as mechanical extraction and chemical treatment have been introduced. This is very important when using dew or water retting process. The reaction time must be carefully evaluated because excessive rating can be cause difficulties for the separation of individual fibers or may weaken the fiber strength. This is about dew rating. In the dew rating method, that is the extraction method, the stems of the plants were cut and evenly distributed in the fields where the presence of bacteria, sunlight, Atmosphere. This is about dew rating. In the dew rating method, that is the extraction method, the stems of the plants were cut and evenly distributed in the fields where the presence of bacteria, sunlight, atmospheric air, and dew causes breakdown of its cellulose tissues and adhesive substances that surrounds the fibers. This process is preferred in locations having heavy night dew and warm day. This process is economical and is widely used for industrial production of blast fibers such as jute and kinaf. Next is water rating method. The next is mechanical rating. This is about dew retting. In the dew retting method, that is the extraction method, the stems of the plants were cut and evenly distributed in the fields where the presence of bacteria, sunlight, atmospheric air, and dew causes breakdown of its cellulose tissues and adhesive substances that surrounds the fibers. This process is preferred in locations having heavy night dew and warm day. This process is economical and is widely used for industrial production of blast fibers such as jute and kinaf. Next is water retting method. The most widely practiced method is water retting process, where bunches of the plant stems were submerged in water. The water can penetrate into the central part of the stem and swells the internal cells. This results in the bursting of outer layer of plants. For natural water retting process, we can utilize like ponds or slow streams or rivers. Note that the water retting process generates low quality fibers. Also, the water retting is a long term process and potential of water contamination prove this method to be less attractive for industrial applications. And the next is mechanical retting. In this process, the outer layer of the fibers, such as gums and stem skin, are eliminated by continuous feeding of the fibers into machine. Later, the extracted fibers from machine are repeatedly washed with water and dried for 48 hours in sunlight, eliminating the water content from the fibers. The mechanical extraction or mechanical retting process of fibers produce high quality fibers with shorter retting time. However, in respect of dew and water retting process, that is previous process, this technique is more expensive. Processing of plant fibers. The designing environmentally friendly materials from natural fibers represents a great challenge in last decade. However, the lack of fundamental knowledge in processing of natural fibers to fabricate the composite structures is still major challenge for potential applications. This is because of hydrophilic behavior of natural fibers, which means moisture absorption behavior, and the raw fibers are processed by chemical treatments or surface treatments. Next, we will move to chemical treatments. As I said, being a hydrophilic behavior of natural fibers and the polymer matrix hydrophobic nature are the main fundamental problems of using natural fibers as a reinforcement for polymer composites. However, by using a chemical treatment, it can remove impurities as well as non-cellulose contents, which can lead the natural fibers allows reducing its fiber hydrophilic nature, and also it can improve the interfacial adhesion between the fiber surface and the polymer matrix. The various chemical treatment, the first one, the alkali or the NaOH treatment. The natural fibers treated by NaOH is very common nowadays. This covers four different practices. In the first practice, both NaOH concentration and the period of time are constant in this process for the chemical treatment of natural fibers. That means in the first practice, both the NaOH concentration and period of time are constant. And the second practice, the NaOH concentration is different for constant period of time. And in the third practice, NaOH concentration is constant for different time periods. And in fourth and last practice, Both NaOH concentration and period of time are different. The second and third practices methods are the most common treatment. That is, NaOH concentration is different for the constant period of time, and NaOH concentration is constant for different time periods. These two are most common treatments to determine the optimal condition for natural fiber modification. At the different NaOH concentration with a constant period of time, the fiber should be treated with 2 to 5% NaOH solution as per the literature. And as the constant NaOH concentration with the different type grades, the natural fibers are treated in maximum 5% NaOH solution. Generally, 5% is optimum for most natural fibers, varying by the time, like 15 minutes, 30 minutes, 45 minutes, 60 minutes, 75 minutes, and 90 minutes. This alkaline treatment permits to eliminate hemicellulose and other waste materials that leads fiber become rough, which can help to improve the interfacial property between fiber and matrix. After any chemical treatment practice, the natural fibers are washed with water and dried in sunlight or in oven. This is the most common practice, that is with washing with water and dried in sunlight or in oven after chemical treatment. The next is acetic acid treatment. In this treatment, the acetic acid solution, that is like a 5, 10 or 15 volume fraction, is used to treat the fibers for 2 hours in ambient temperature, that is around 23 to 25 degrees Celsius, to remove hemicellulose and other waste materials from the surface of fibers. Later, the fibers are neutralized by using 0.1% NaOH solution by washing with water and drying at 100 degrees Celsius for 24 hours in oven. And this treatment can enhance the tensile property and initial degradation temperature of fibers. The next is silane treatment. This is also most common treatment. The silane is multifunctional molecule that is used for coupling agent to modify the fiber surface. The vinyl trimethoxysilane silane and aminopropylene trimethylsilane are the commonly used silanes in order to obtain reliable modification of natural fibers. And in silane treatment, it is required some amount of vinyl trimethoxysilane or aminopropylene triethoxysilanes that is mixed with an ethanol water mixture using the ratio 60 is to 40. Later, this solution is kept for 1 hour and pH is maintained at 4 by adding acetic acid. The raw fibers which are immersed in the solution for 2 hours, the treated fibers were later dried overnight at 60 degrees Celsius. This silane treatment can improve the chemical properties of and even physical properties of natural fibers. The next one is benzoxyl peroxide treatment. In benzoxyl peroxide treatment, the natural fibers were immersed in 6% benzoxyl peroxide in acetone for 30 minutes. The treated fibers were washed and dried for 24 hours. And the effect of treatment is this treatment helps to enhances the adhesion mechanism between the natural fibers and polymer matrix. The next is potassium permanganate treatment. In potassium permanganate treatment, the raw natural fibers were immersed in 0.5% potassium permanganate in acetone for 30 minutes. And same, that treated fibers were washed and dried for 24 hours. And by this treatment, this will enhance the chemical or physical properties of natural fibers. Stearic acid treatment, the next one. For stearic acid treatment, a solution of 1% stearic acid in ethyl alcohol was used. This solution is later poured slowly into the natural fibers, placed in the glass vessel with a continuous stirring. The treated fibers were later dried at 80 degree for 45 minutes in oven. The next is seawater treatment. It is another simple and economical method to modify natural fibers. Indicates the use of seawater. Firstly, the pH of seawater and salinity need to be checked. Later, the fibers could be immersed in this seawater for up to 30 days. And finally, the fibers are washed with water and dried at ambient temperature. And the next is cellulose powder treatment. The preparation of natural fibers with the cellulose powder assume that the fibers are soaked separately in steel container containing 2 to 10% of cellulose pulp, and it is prepared with the hot distilled water for up to 30 minutes, and later we can treat the fibers and dried at 70 degrees Celsius for 3 hours in oven. And it provides a good wetting chemistry, means the interfacial bonding between natural fibers and the matrix. The next is polymer coating. The solution of polymer made from 12% of A mixture, that is 48% A mixture means 48% acrylic acid plus 42% water, 8% sterling, and 1.5% ethoconic acid, and 2.5% acrylic diphenyl oxide disulfonate with 1% and with 1% of B mixture. That is, B mixture is consists of 7.5% sodium persulfate and 92.5% water. And along with B mixture, that is along with A mixture, B mixture, then 1% of anilonic sulfurate and water, 85% were mixed with 14,000 rpm at 80 to 82 degree Celsius for 3 hours. Later, the fibers are immersed in this mixed polymer solution for 30 minutes. Finally, the fibers were filtered and then dried for 44 hours at 60 degree Celsius. Next is bleaching method. For bleaching, the natural fibers are being treated with CaClO2, that calcium hypochlorite, for 45 minutes. The bleached fibers are then washed with deionized water and then dried for 24 hours at 80 degrees Celsius in a oven. Some more chemical treatment are there, such as graft copolymerization and isocyanate treatments were also used to reduce hydrophilic nature of natural fibers. Next, we will move to surface treatments of natural fibers. The natural fibers require some surface treatments in order to improve its surface performance. The chemical treatment are aimed to reduce the hydrophilic nature of fibers, as we discussed in the previous slides. But the surface treatments may not only modify the fiber surface but also increase the fiber strength, which leads to improving the adhesion mechanism between fiber surface and polymer matrix. And despite the importance of surface treatment, there are limited amount of approach used to tackle this challenge due to lack of availability of surface treatment equipments. And the most available surface treatments are plasma treatment, vacuum ultraviolet irradiation treatment, ozone treatment, corona treatment, gamma ray treatment, laser treatment. These are all most commonly used surface modification treatments. But These treatments are very costly. Next, plant fibers. This is a section. Second section is dedicated to present most useful characterization methods of natural fibers. The characterization methods are very essential in order to select the natural fibers suitable as reinforcement for polymer composites. And this table shows physical, chemical, and mechanical properties of natural fibers. And now I would like to explain how to measure physical properties such as diameter and density, tensile properties, and chemical analysis. In practice, the measurement of diameter of natural fibers is made using a digital micrometer or by a microscope, either optical microscope OM or SEM, scanning electron microscope. The use of digital micrometer permits measures within an accuracy of 0.001 mm, 0.001 mm. Otherwise, measurements by an air wedge, that is plus or minus 0.001 mm, is another alternative technique. And the density of the fibers can be measured by piconometer. The natural fibers tensile properties are driven by three main factors such as test parameters, conditions, and type of plant fiber and the fiber dimension. Fiber dimension means thickness, width, and length on the cross section. The fiber should be tested under tensile loading by following the STM C1557 or STM D382207 standard using the universal testing machine in order to obtain the high precision. And it is recommended to perform the test with the servo electric tensile machine with a 5 kilonewton load cell or less than 5 kilonewton load cell. And for chemical measurement of fibers, the method of Kushner and Ofer to measure the hemicellulose contents of the fibers, and lignin is usually calculated by Apida method. The TAPI method is used for record the ash content, and while the wax content is determined by the Conard method. XRD, X-ray diffraction analysis. XRD is a non-destructive and a rapid analytic technique that is mainly used to identify the crystallographic structure and chemical composition of natural fibers. Usually, the X-ray diffraction allows the natural fibers, particularly natural fibers, to be scanned in a 2 theta range, while theta is the Bragg angle, and this 2 theta range varying from 10 degree to 50 degree. And see that right figure, it shows the X-ray diffractograms of untreated and treated plant fibers. Untreated means raw fibers, and treated means that is any treatment, like here we are consider alkaline treatment. It is clearly shows two peaks of each specimen respectively. The first peak represents the diffraction angle, that is 2 theta is equal to 16.02 degree and 15.90 degree respectively for treated and untreated fibers. For treated it is 16.02 and untreated 15.90 degree. The peak at about 16 degree usually attributes so that it's a amorphous constituents. The second high intensity peak observed at see that the 2 theta is 22.034 degree and 22.02 degree for that is treated and untreated fibers respectively. The peak at about 22 degree belongs to the crystalline constituents. It means around 16 degree is for amorphous constituents and 22 degree is for crystalline constituents. From the obtained X-ray diffrograms, the crystalline index, that is Ca, is calculated using the intensity of crystalline phase and the amorphous phase respectively. The next is Fourier transform infrared spectrometry, that is FTIR. FTIR is considered a non-destructive analysis that can provide quantitatively and of course qualitative details of natural fibers. An infrared absorption spectrum is obtained from chemical composition of natural fibers, and the FTI spectrum obtained from natural fibers is principally absorbed in the range 400 to 4000 centimeter inverse frequency, and based on the peak position and its corresponding